Okay, so we are going to be looking at exponents again. So we're just going to review a little bit of exponents from the other day, and then I'm going to introduce essentially a new law. So this would be page 101 in your enhanced textbook, okay? If you want to follow along. Okay. So when we're looking, we are looking at a base, an exponent, and we refer to all of that as a power, okay? So again, this is just a little bit of review before we get into some material here. So 8 to the power of 7 is really like saying 8 times 8 times 8 times 8 times 8 times 8 times 8, 7 times, right? I'm not going to spend too much time on that, but you don't have to write down this if you know it because it was on the previous notes, okay? But I am going to have this page here, okay? Just a reminder, when we're looking at negative 2 to the power of 6 and bracket negative 2 to the power of 6, those have different meanings, right? The exponent applies directly next to either the variable or the coefficient it is, okay? It only applies to, say, a coefficient in like a situation here, okay, where the bracket is around, so it's around the negative. So example 1, no bracket, okay? The negative is on the outside, and we're just using 2 to the power of 6, okay? So our answer would be negative 64. Okay? Now if we have, come on in. Okay. Now if we have negative 2 to the power of 6, okay, in brackets, it's like saying negative 2 times itself 6 times, okay? Those that just came in, we're just reviewing a little bit of the exponent stuff before we dive into some new material, okay? So we have something called exponent laws, which is what we worked on yesterday. So we have the multiplicative law. What happens in the multiplicative law? What happens here? What happens to the exponents? Yeah? Yeah, you add the exponents together, okay? So here is the long version, okay? But if we were just to look, again, I'm not spending too much time on this because I went through it in detail last night, okay? We would add the exponents, okay? So that's a review from yesterday, okay? Any questions on that law? Just a reminder, okay? We're not going to look at the proofs. So we have a couple of more laws we can look at, okay? So quotient law or division law here, okay? So if two values are dividing, what operation we're using in the exponents? Subtraction, okay? Power to power, okay? Power to power, what happens with the exponents? You multiply them, okay? If we're looking at, so these are, it's not really new. We touched on this concept yesterday, okay? It's just we're giving it a name now, okay? So we have the distributive law, okay? So all it's saying is that exponent applies to everything that's within a bracket. But is that new? Like we went over that yesterday. So that's not really new. We're just giving it a name. We're going to call it the distributive law, okay? I'm not going to ask you to identify the laws. I'm not going to be like, what type of law does this demonstrate? I'm just going to ask you to either simplify or solve questions like that, okay? Distributive law 2, okay? It does work with fractions, and we do need to look at fractions, okay? So the exponent in this situation would apply to both the top and the bottom, okay? So this is what we would end up with. And this is, you're going to get time to work on some questions like this today. So harder questions in class with your peers. So that's why we're doing a second day of exponent laws, okay? Any power, okay, so any variable or any coefficient to the power of 0 is 1. We're good with that one, right? Okay. And then this is the new one that I kind of want to go over here, okay? If you have a negative value, because some of you would have got negative values in your homework last night, and that's fine, okay? So the negative value is fine. Now we have to teach you how to put them into a positive value, okay? So when it's a positive value, okay, when it's negative, I'm just going to zoom in here, okay, you'll have a negative in the top, okay? Now, to make it positive, you make it the reciprocal, okay? So we put whatever our value is here, okay, under 1, and we apply our exponent to that, okay? And then from here, if you want to evaluate it, you could, okay? So that's the big new one for today that I'm going to have you work on a little bit, okay? If you want to, you can have a look at this video, okay? I don't know if I can bring it up. No, it's not going to work on mine. But you guys can totally watch that video. You are not expected to, I would not test you on that, but if you want to know for further information why, we can do that, okay? So what I'm going to have you work on, okay, so these are just questions. So this is what you're going to work on. You're going to read, okay, 106, okay, so you're going to read, okay? And I encourage you to work with a partner here. You're going to read 107, okay? They're just examples, okay? Read 108. There's just one example on each page, so it's 3 examples you're reading through. It's not going to be bad. And then I would like you to work on question 1 to 3, okay? So this is going to be your homework, okay, here. And then what you could do, if you finish those while other people are still working, you can attempt some of the enhanced questions, okay? How long do you guys think you guys would need for this to get through that? You can work with partners. So essentially, I'm giving you time to get this portion of the homework done because I'm going to teach another lesson today. How long do you guys think you need for that? Half an hour? Pardon? 20 minutes? How about we just say half an hour? And then we'll reconvene at half an hour. Feel free to move your desk. Work with a partner, okay? So this is on the enhanced textbook, page 109, okay? And then we will reconvene this lesson, okay? And we're going to be looking at exponential models. So something a little bit tougher. Because essentially we've done a lot of this yesterday. Okay. So we are moving on to the second part of the lesson. So this is the homework for that lesson. So 2.4, I will post that. And we are moving into exponential models. The nice part about exponential models, guys, you will look at that in math again, exponential models. You will also use these models in science, okay? So they're going to cross over between your 2 subjects, which is nice, okay? So if you understand now, you'll have a better understanding later. So we're going to look at what we call growth and decay models, okay? Growth, right? We're kind of looking at models that work upwards exponentially, okay? So that would be growth, essentially. And then we also have what we call decay models, okay? Is they exponentially work down. And these are graphing, and eventually, in your high school career, you will work with graphing exponential models, okay? Right now, we're just kind of understand them from a math perspective to solve some problems. So they have a little example which we'll kind of work through on the calculation, but then we're actually going to look at another example. So the Woodlands Bank of Mississauga offers an exciting new investment offer. The detail of this offer are the amount invested will double every day that sits in the account. Kate decides to invest 1 penny into this account, okay? So first of all, you have to kind of identify, is this a growth or a decay model, you guys think? It's going to be growth, yeah. Okay. So what they would like to know is how much money will be in Kate's account after 30 days, okay? Or then how long will it take for Kate to have invested or to have saved $1 million, okay? So what we would typically have you do is we would have you work with a chart just to kind of look at some ideas here, okay? So day 1, right? Kate has 1 cent in her bank account, okay? On day 1 here, they would double the 1 cent, right? So now Kate has 2 cents. Day 3, or day 2, sorry. Day 2, because she has 2 cents in the account, 2 cents doubles, right? So it becomes 4. So are you guys seeing how this is doubling? You guys are seeing this? Okay. So it's not like a nice linear equation where it just goes up like this, okay? So that's not happening. We're looking at something that's rapidly increasing, okay? So we need to develop a way to look at it that way. Just gonna move on to the next, okay? So if we were to kind of just continue through that Google Sheet, that form, if we were to continue here, okay, we would just keep taking the amount from the previous day, doubling it for the next day, okay? Again, I'm not having you do this, so I'm going to give you guys the answers, and then we're going to actually do another example, okay? So if we were to continue to do this spreadsheet, okay, and again, this is something if you really feel like you would like to try at home when we have a little bit more time, or even at the end of class, if you'd like to try that with a spreadsheet, we can do that, okay? So after, if we did this for 30 days, so if we worked from 10 and continued on for another 20, Kate will have $10 million, $737,418.24. So not bad for a month's worth of investment, right? After the 36 days, the account holds $671,000, and on the 27th day, Kate will have $1 million. Okay, so it just kind of shows you how your money can double very, very fastly. Okay. What I do want to get into now is how we develop the formula for that. Okay, what are we actually going to work with? Okay, so developing an algebraic model. Okay. So this is the idea behind that question here. So we have our days, okay? We have the amount, the money is continually growing every day. And what we're really looking at is that we are working with exponents, okay, to solve this. Because what we're saying is based on that 1 cent initially invested, we continue to double up on that by multiplying by a power of 2. And we know, okay, based on exponent laws, right? If I did 2 to the power of 1, okay, times 2 to the power of 1, what would be my new power? Yeah, 2 to the power of 2, okay, which is what they're representing here. So they're slowly accumulating by just adding another power. Okay, they're showing that model here, okay? So what we do is we can actually represent, okay, a formula. Okay, so we could say let t represent the time in days. Okay, so that is our exponent. Okay, 2 would be our growth or decay. Because it's doubling, that's why we're using the value of 2. Okay, so this would be our growth or decay. And then 0.01 is what? Can anybody tell me what was that initially with our problem? What was this 1 cent?
Initial amount.
Yeah, the initial amount. Excellent. Okay. So they put values in it. Okay. Sometimes how we'll represent it another way would be like A of t, so that's just like whatever t is for time frame will represent your answer, okay? Would be like saying your initial amount, okay, times b to the value of t. Sometimes we'll use different variables to represent that, but A always represents the initial here, okay? B represents your growth or decay rate. Okay, and then T represents your time. Okay, So if we were to look at, instead of using a spreadsheet model, okay, we wanted to answer that one question, okay? So we can input, okay? So we want to find out what was the value, the amount at 30 days, okay? Well, the initial amount we put in was a penny, okay? We are doubling, okay? And we did this for 30 days, okay? Make sure you follow order of operations, okay? You start with working with the exponent, so 2 to the power 30 times 0.01, okay? And we get our final amount, okay? I'll give you guys a second. Is there any questions? We're going to look at another example too. Is there any questions about that so far? Okay. No? Not too bad. Because you will be asked, you will have to develop your own formulas. So you will be working with this, okay? That's kind of like your base. Start with your base, okay? I'm just going to give people a second. Some people are writing this down, okay? I will post this video lesson too for later, so it will be posted. Good, I just see some pencils going. That's no problem. So to use this equation to determine, so this is part B of our original question. They want to determine, okay, when will they reach $1 million, right? Okay. So what does $1 million represent in our equation? So say I had A equals A times B to T. What does, if they're asking you for the end amount, so $1 million, what variable up there does it represent? Jan, you get your hand up? Not B, because it's the end amount. Think about this. Yeah, AT. It represents the final amount you're trying to solve for, okay? So what we could do is we can put this in to try to solve for that, okay? So as you can see here, what they've done is they put in $1 million into the AT position. What we're trying to do now is we're trying to isolate to solve for T, okay? So we're going to move everything to the opposite side, right? So that's why they start with the division of 0.01. They cross that out on this side, and you're left with $100 million on the other side. So at this stage, this is where it can get a little bit tricky, because typically I would teach log, okay? But we're not going to really go into log. We're just going to use more like a guess and check method here, okay? What they're looking at is here, 1, 2, 3, 4, 5, 6, 7, 8, okay? So they're kind of looking at it as a 10 to the power of, okay? And we are going to look at some power of, some base representations in our next lesson here, okay? So we can only get so close in this method unless I actually teach you log, which I would say, like, if you put 10 to the power of 8 equals 2t, we can try to break it down to solve, but it won't happen. You won't be able to even solve it that way, okay? So I will go into that. So you'll see what they've done here is they've said 10 to the power of 8, okay? Is 10 to the power of 8 $100 million? You can check it on a calculator. Just try it out. No? Yes, it is. It is, that's right, okay? So that's where they got down. So then what they were trying to do in this situation is, can they break this 10 to have the same base? Because you know when we talked about exponents and we talked about solving exponents, we talked about having the bases the same, right? So that's that idea. And you will get into this math. You probably, because you're in the enhanced course, you'll do a little bit of this next year. You'll definitely touch on it in grade 11. Okay, how to solve exponents that way. Okay. So what we do then, okay, is they start to use a substitution value, okay, to kind of look at this. So see, in these questions, they're substituting T26 and T 27. So they're really just doing a guess and check. Okay? So they found out 26 days, okay, is under $1 million there, right? But 27 days is over $1 million. So we know that our answer falls somewhere in between. Okay? So sometimes the guess and check method is still valid until we teach you some more of the harder stuff here. Okay? I'm just going to move on to the next slide, okay? This is a half-life question, okay? So it's the same idea. So we've done growth, we've looked at growth. Now we're going to look at what we call decay, okay? In science, a lot of times we'll look at chemicals and we'll be like, they have a half-life, okay? Or the radioactivity has a half-life, okay? So you will do questions like this in science, I guarantee it, okay? So let's just look at this example here, okay? The half-life of a substance is defined as the amount of time that it takes for a substance to lose half of its mass to pure energy. The half of the plutonium, 241, okay, is measured by approximately 14.4 years. If one were to have a sample of 100 grams of plutonium, okay, 241, how much of the sample would remain after 5 years, okay? So when we're setting up this equation, okay, we are looking at, okay, a decay model here, okay? So this is example, a decay model where we're working downwards exponentially, okay? Our investment question, we were working exponentially up, okay? So let's come up with a formula for this. It essentially is given to you, okay? So we can look at this, okay? So the initial amount, okay, of the plutonium was, what was it? You read through the question. You got to read, might have to read it again. What was the initial amount? Was 100 grams, right? So that's our initial amount, okay? If we look at our growth or decay, so this is our decay, right? It was a half-life, okay? So we don't really want to use a fraction in this sense. So a half is just represented by 0.5, right? Okay. And then here's something you have to understand, because this is where it kind of gets a little tricky for half-life, because they give you a time, okay? So S has one extra step, okay? Because what was so special about S? Can someone read that out again on the question for me? What was so special about the half-life on that original question? Okay? The half-life of plutonium is measured by approximately 14.4 years. So what they're saying is it takes 14.4 years for the half-life to occur. Okay? So when you're using time here, okay, or they're gonna use S, okay? Whatever time they're initially asking you for, so let's T, okay, has to be divided by the 14.4 years because that represents the half-life, okay? And then now you could put that into your equation. So, for example, they want to know what was the half-life at 10 years, right? So that's why they ended up doing 10 divided by 14.4 equals approximately 0.69, okay? So we would now put that into our equation here, okay? And now we can solve, okay? So how much plutonium is left after 10 years? Well, about 62, okay? 62 grams, right? That was our units. So 62 grams of that sample was remaining. So decay can just be a little bit harder, but they can even do this in growth rate just because sometimes there's this extra step, okay, where you have to think about what is actually the half rate. It doesn't happen every day, doesn't happen every year, that happen every so many days, right? So that's important too, okay? Say the half-life is, I don't think it's in one of these questions. say the half-life is in days, like it happens every 30 days, the half-life, okay? Well, if I say find out the half-life of something in a year, right? You have to convert, you can't just put 1 divided by 30, right? Because that's not the same unit. I'd have to put the year into the same unit of days before I put it back into that equation. Okay? So just make sure your S, you're using the same units for that. Okay? That's my little hint. That's a little, because I don't even think you guys touch on it, but for future use, when you guys get into your older classes, you guys can seem like super smart, like you already knew that. Okay? That is all. They just do another map here. Okay? On percents. So what I'm going to have you guys do is I'm going to have you guys work on a couple of questions here. Okay? Let's look at 2, 3, 4, and 5. Okay? Now the one thing you need to notice is some of these are given to you in percent. Okay? So some of those are given to you in percent, okay? So this has an increased factor of 35%. So think of it like when we are doing our math question for money, right? If something is needing to grow in a calculation, okay, if I still need to put that in a decimal number, I wouldn't put it in as 0.35, okay? Because that's only going to give me part of the whole. I need to put it in as 1.35 to show that there's a growth occurring. Okay? Now, for example, and I'll use this because you actually decided to do this on your test. This was good, okay? So something's depreciating by 30%. What is it actually part of? What's the part of it? 60%. Not 60.
No. I made a mistake.
I know. No, but this is exact. I know you made a mistake. It's all right. But what I'm saying is, how do you look at it? You don't look at it as a part of 30%. You look at it as a part of 70%, right? So you would say 1 subtract 0.3, and you would use 0.7 to show that it's depreciating, if it's a percent. Okay? So I just wanted to give those little hints for that. And question 4, yeah, look at this one. Or question 5, okay? It doubles in size every 30 minutes. But my question asks you 24 hours, right? So make sure you convert the 24 hours into minutes. I think those hints, I think that's all I need to give you for hints, okay? So I would like you guys to try those 4 questions, okay? On just these 4, okay? Just really picking them down. On page 120. So really, it only ended up you have 7 questions for homework tonight. You have the rest of the period to work on this. Feel free to work with friends, okay? I really like when you're working with friends. So you can either start working on those or you can finish the exponent questions.